Hi, and welcome to Week 14, Mini Lecture 1 for the Quantum Universe for Educators. In this lecture, I'm going to talk about the concept of quantum paths. I'm going to use that to introduce the two types of particles that exist in nature, fermions and bosons, and then I'm going to talk a little bit about quantum field theory in general and what it actually is. Okay, so let's go back to the double slit experiment, where we're going to have a source of electrons fired at two slits, and we can ask what is the probability that we'll detect an electron at some position A on a slit behind the double slits. And we've seen that the total wave function for an electron traveling from the source of the slits to a position A is given by a wave function that describes the path going through slit 1 plus the wave function that describes the electron going through slit 2. And the probability that we find an electron at A is then the square modulus of this wave function. So if we don't look at which path the electron takes, the electron in a sense takes both paths at once. Now we could add a third slit to this. If we fire an electron at 3 slits, then if we don't look to see which slit the electron takes, then the wave function is described by the sum of a wave function that describes the electron going through slit 1, a wave function for slit 2, and a wave function for slit 3. So the electron takes all 3 possible paths at once in order to get to A, if we don't look. And again, the probability is the square modulus of the total wave function. So you could keep on going, you could keep on adding slits to this central barrier here and increasing the number of ways and the number of possible paths the electrons could take. You could imagine keep going until all you have left are slits and the barrier no longer exists because you've just filled it full of slits. This is the limit of infinite slits. And again, the wave function that describes the electron moving from the source to position A on this screen is given by the sum of all possible paths the electron can take. So if there are no slits there, then this just corresponds to an electron freely traveling from the source to A. And this says that the electron can take any possible path between the source and A, and in fact takes every possible path between the source and A. In order to end up at A, we have to take into account every possible path that the electron can take. Now, if we have a sum of infinite terms, calculus tells us that such an infinite sum can be represented as an integral. An integral is essentially an infinite sum. So we could represent this as an integral over all of space, and for each point in space you have a wave function which describes the probability of the electron taking a particular path that goes through that point in space. So this is just another way of writing this infinite sum on the previous page here. So this is an integral over all possible paths, a sum over all possible paths the electron can take, so it is called a path integral. And Richard Feynman in 1948 came up with a way of mathematically describing quantum mechanics. There was the path integral formulation based on path integrals like this. This is just an alternative way to the Schrödinger and Heisenberg pictures of quantum mechanics. So the bottom line here is that when an electron moves from one point to another, it takes every possible path to get from that one point to the other. The probability that an electron travels between 2 points, the probability of the electron getting from here to there, as it were, this is called in the business the propagator. Okay, now we're going to introduce the concept of fermions and bosons. Now let's suppose we have two sources of particles, S1 and S2, and they both emit a particle, and we're going to detect the particles at A and B. One of the particles ends up at A, one of them ends up at B. Well, there are two possibilities. You could have a particle emitted by source 1 that ends up at A and travels there via this route, and you could have a particle emitted by source 2 ending up at B, both of which are associated with a particular wave function. And so the probability of detecting a particle at A and a particle at B is just the sum of these two wave functions, and the probability is the square of this wave function here. But there's another possibility. Okay? The particle emitted at S1 could end up at B, and the particle emitted by source S2 could end up at A. The probabilities for these two paths are given by two different wave functions, and the probability that we detect a particle at B and a particle at A that were emitted from sources S1 and S2 respectively is given by the sum of these two wave functions, and the probability is the square of this wave function. So here's the thing though. But we can never know which path the electron takes, and all electrons look alike, so we don't know which of these two paths actually occurred when we detect a particle at A, say an electron, and a particle at B. So that means the probability that a particle was emitted by source 1 and ended up at A, and source 2 ended up at B, should be equal to the probability that the source 1 particle ended up at B and the source 2 particle ended up at A. They have to be the same because there is no way to distinguish between them. So that means the square of this wave function corresponding to particle 1 at A, particle 2 at B, should be equal to the square of the wave function corresponding to particle 1 ending up at B and particle 2 ending up at A. Or take the square root of this and you get that the state of particle 1 ending up at A and particle 2 at B is equal to plus or minus the state corresponding to particle 1 ending up at B and particle 2 ending up at A. So there are two possibilities here, a plus and a minus sign. If the two states are exactly equal, then they describe particles that are bosons. And it turns out that particles that obey this relation have integer spin, like photons, for example. So their spin is 0, 1, or 2, or so on. So bosons are particles with integer spin. So when you switch the two particles' places, the state doesn't change. But there's another possibility that if you swap the particles around, the wave function changes sign. So the state AB is equal to minus the state BA. Particles that obey this relation are called fermions. Bosons and fermions are named after the physicists Bose and Fermi, who came up with these. And it turns out that fermions have half integer spin, just like electrons, protons, and neutrons do. They all have spin a half. So half integer spin particles are fermions, integer spin particles are bosons. But there's more. Let's suppose that the 2 points A and B, we move them closer and closer together until they become the same point. So in other words, the particles emitted at S1 and S2 both travel to the same point, A. Well, if the particles are fermions, then if you switch the particles' places, the state changes sign. You get a minus sign in. But if they're the same points in space, then we know the state has to be equal. So there's only one possible solution to this equation. If the states are equal, but also equal to minus each other, that means the state has to be equal to 0. So this tells us that it is impossible for two fermions to exist at the same point in space. There is 0 probability that you will detect two fermions at the same point in space. This is just the Pauli exclusion principle which we encountered a few weeks ago. Right? This is why only one electron can occupy each orbital in atoms, because there is 0 probability of finding two electrons occupying the same orbital, the same state, or the same point in space. So we've just explained the entire periodic table and all of chemistry in about 4 minutes, which is not too bad. Okay, we're going to round off this mini lecture by introducing quantum field theory, at least conceptually. Now, in classical theory, forces are caused by fields which permeate all of space. So electric fields, magnetic fields, gravitational fields. We're familiar with these from classical physics. So the question is, what happens to these fields when we try and describe them using quantum theory? Well, of course, wave-particle duality says that fields, which are wave-like things, they're extended through space, also have a particle-like nature. Okay, quantum theory says things aren't just fields or particles, they're both at the same time. So all fields have a particle associated with them. And we've already encountered the particle that carries the electromagnetic force. It is the photon. And it turns out that when you describe something like two electrons repelling each other because they have like charges, then what is happening is they are exchanging photons, specifically virtual photons. Right. We'll be talking a lot more about diagrams like this in the second mini lecture. But this just shows two electrons moving through space and they exchange a photon. And this causes a repulsive force between them. So this is one of the first basic predictions of quantum field theory, what you get when you apply quantum theory to fields. Next time you attach a fridge magnet to a fridge and feel that attraction there, what's happening is that the fridge and the fridge magnet are constantly exchanging these virtual photons. They're virtual photons because, and you'll learn about what makes a photon virtual versus real in the reading that you'll do this week. The second prediction of quantum field theory is that all particles have antiparticles. These are particles that have the opposite properties to normal particles, except their mass and spin. So antiparticles still have regular mass, an anti-electron still has the mass of an electron and the spin of an electron, but it has an opposite charge. An electron's charge is negative, of course, so an anti-electron is positive, and we call it a positron. The photon has no charge, which means an antiphoton is the same thing as a photon. The third consequence of quantum field theory is that particles that actually make up matter, everything around us, are fermions. Okay, so electrons, protons, and neutrons, which build all of the atoms that make up the matter that we see, are all fermions. But particles that carry the forces of nature, like photons, which carry the electromagnetic force, they are all bosons. They have integer spin. So nature is divided up into matter, made up of fermion particles, and forces, which are caused by boson particles. A final important consequence of quantum field theory that you'll also encounter in the reading this week is the fact that even empty space is not actually empty. The uncertainty principle tells us that we cannot say for sure that empty space is empty, and on very short time scales, particle-antiparticle pairs pop into existence from nothing and then are immediately annihilated and destroyed again. These particles are those virtual particles that we encountered, that I mentioned previously. And if you supply enough energy, you can turn these virtual particles into real particles. Now, quantum field theory began to be developed pretty soon after quantum mechanics was in place in the late 1920s, led by Paul Dirac, who also came up with the notion of antiparticles. Antiparticles, incidentally, were discovered first in the 1930s. The first complete quantum field theory to be developed was the theory of how electromagnetic fields interact with matter, which is essentially boils down to how electrons interact with photons. This theory is called quantum electrodynamics, which is usually shortened to QED. And there's a nice symmetry here that the development of quantum electrodynamics finally completed the theory of how electromagnetic fields interact with matter. This was one of the big goals of classical physics in the 19th century, and it was a thing that led Max Planck to introduce the quantum in 1900, examining how black body radiation, which is one manifestation of electromagnetic fields, how that interacts with matter. QED was finished in 1950, so about 50 years after Max Planck introduced the quantum, we finally came up with the complete description of how electromagnetic fields interact with matter. Okay, we're going to finish up by going over the fundamental particles that make up nature. Now, it turns out that neutrons and protons are made up of more fundamental particles called quarks. Quarks come in 6 varieties: up, down, charm, strange, top and bottom, and the first quark was discovered in the 1970s. This table lists their charges and their spins. They're all fermions because they make up matter. A neutron is made up of 2 down quarks and an up quark, and a proton is made up of 2 up quarks and a down quark. Now, quarks are fermions, and they're fermions that feel the strong and weak nuclear forces. So the strong nuclear force is the force that holds protons and neutrons together and holds the nuclei of atoms together. And the weak nuclear force is the force that's responsible for radioactive decay. On the other hand, down here we have the leptons. Now, leptons are the name that we give to fermions that do not feel the strong nuclear force. The lepton that we're most familiar with is the electron, but there are also 3 varieties of neutrinos and 2 other leptons, a muon and a tau particle, which we see generally only in cosmic rays and in particle accelerators. Now, all of matter around us is actually made up of only 3 particles, up quarks, down quarks, and electrons, which are all from this so-called first generation of fermions. There exist these other 2 generations of fermions, of particles, that we only ever see in cosmic rays and particle accelerators. And it's somewhat unknown why that is, why matter is only made up of this first set of particles. Now, as we mentioned before, the forces of nature are carried by bosons. So the electromagnetic force is carried by photons, the strong nuclear force is carried by gluons. So neutrons and protons are held together in nuclei by exchanging gluons with each other. The weak nuclear force is carried by 3 bosons, the W+, the W-, and the Z0 particle. There is another field in nature which has become quite famous recently, the Higgs field, which causes inertial mass. In other words, it causes resistance to motion when you apply a force to a particle. And again, it is a field, so there must be a particle associated with it, and that particle is the Higgs boson, which was discovered in 2012.